Good evening and welcome again to Public Perspective. I'm your host, Kevin McDermott. And tonight we're going to delve deeply into something that most people probably never think about, and that is the subject of physics, particle physics. We'll explain what that means. Experimental physics, we'll explain about that too. And generally, we'll do our best not to confuse everyone who's watching the show. So my guest tonight, Dr. David Christensen from FermiLab, which is actually called the Fermi National Accelerator.
Yep,
Lab.
we are the FNAL is the Fermi National Accelerator Laboratory. So when it was first founded, it was just the National Accelerator Laboratory, and then in honor of Enrico Fermi, and who's of course got the big Chicago connection,
Yes.
It was renamed relatively early on to Fermi National Accelerator Laboratory, or just FermiLab.
Which I think most people around Chicago have heard the term FermiLab.
Right,
That's what,
exactly.
Yeah. So let's, in deference to our audience, let's start with some really basic stuff. So you are a research scientist at FermiLab, and this is, your area is particle physics.
Mm-hmm.
What is that?
Okay, so we have to go a long ways back and probably remember what people learned in high school and then in college, if you took that kind of subjects in college. Stuff like tables and everything is made of molecules, and the molecules in turn are made of atoms.
Mm-hmm.
And atoms have most of their mass concentrated in a very, very small volume in the center of the atom. That's called the nucleus of the atom. And then all the chemistry is determined by electrons, which are negatively charged. The nucleus is positively charged, so electric charges.
Mm-hmm.
And so all the chemistry has to do with the configuration of those electrons. If you look inside the nucleus, you find that it isn't just a point charge, but it has a structure also similar to the structure of molecules or the structure
Mm-hmm.
of atoms. And the nucleus is made of particles called protons, which are positively charged, and particles called neutrons, which in many ways are exactly like protons, but with no electric charge. And they have a relatively complex substructure that makes up the nucleus.
And there's a whole menagerie of subatomic particles.
Right, because if you actually then, try to understand sort of what's the nature of a proton, you find out relatively quickly that protons and neutrons also have a substructure.
Mm-hmm.
And that's a pretty complicated substructure. Now, in order to see what the structure of something that's on that subatomic level, I mean, these things are really small,
Yes.
You need a specialized microscope. And the microscope is a particle beam. So the microscopes of particle physics are accelerators.
And these are enormous machines, these accelerators.
The first ones were relatively small. I mean, the first cyclotron was something you could hold in your hand.
Really?
And yeah, that was Lawrence's first machine was literally this size.
That's there's a Lawrence Berkeley lab that's named after Dr. Lawrence.
Right, exactly.
Okay.
They got bigger and bigger. The first accelerators were developed in the 40s,
Mm-hmm.
and then after the war there was an explosion of the science of building accelerators. And
So if I can interrupt you for a second. So the accelerators are how the atom was originally split. And we talk about splitting the atom, which was a precursor to nuclear weapons, the atomic bomb.
well,
Right?
actually, so the atoms, mostly when you're looking at atoms being split and things like atomic weapons, you're using materials that are already radioactive. And if you get the atom splitting that is observed is just, it's not driven by an accelerator, but
Okay,
something
yes,
which just happens.
It happens in itself because of the way the material is.
And
right.
so they're happening in nuclear reactors.
So would the explosion in interest in accelerators, was that in any way linked to the development of nuclear weapons in World War, well, they weren't called nuclear weapons, but the atom bomb in World War II. Did that drive any of this, or was it really two separate paths?
It's really separate paths. The basic science was being developed using probes from accelerators, or actually the first atomic beams or beams that were used in atomic physics were once again beams made from radioactive materials. So the original Rutherford scattering experiments that illustrated atomic structure and discovered basically that the atom had most of its mass in a very, very small central, in the nucleus. These were scattering experiments, but with sort of a natural beam, beam from radioactive decays.
But so now there are these, well, what are now enormous machines like the CERN accelerator.
In order to see smaller and smaller distance scales, you need higher and higher energy beams. And to get the high energy beams, you need physically larger machines.
And I've read about these machines, like CERN is, what is a mile in diameter, is it?
Well, let's see. The FermiLab main ring accelerator was 1 kilometer in radius. And the LHC is about 7 times bigger than that. So it's...
Okay, so it's 7 kilometers radius.
Yeah, right. And I don't remember numbers very well, so that's approximate.
Yeah, okay, no, that's good enough. So these, in other words, it's very large. Yeah. Right. So one of the things I think about, because I have mentioned before, I do read this stuff as a geeky layperson, is that like at CERN, which is in Switzerland, right?
Right, it's outside of Geneva.
So, which is the highest energy accelerator in the world right now. And so they accelerate these protons up to enormous energies. They're almost at the speed of light where they collide. And then they produce all these fragments that are these other subatomic particles that are then measured and analyzed. And they create, like, so for example, the Higgs Boson, something that, as you know, was sought for years and years, and finally was discovered at these very high energy collisions. But these things only exist for a blink of an eye, and then they decay into other things. So what?
And so you don't actually see the Higgs boson. What you see is the long-lived particles that it decays into.
And so my question is, if it's so hard to produce, and they have such ephemeral lives, how can they possibly exist in a manner that allows them to, like the Higgs boson, for example, supposedly imparts mass to all these other particles, right? So how can it do that if it only exists at extremely high energies and only for a blink of an eye moment?
Okay, I understand what you're saying. So how to approach it. So what you're asking has to do with the general field or type of description, which is called quantum field theory. And so let's see, thinking about how to explain what a field theory is. People in school have probably learned about electricity and magnetism and electric forces. And so if you have a charged particle, then there is an electric field that's generated from that charge. And so if I have a charged particle here, then another charged particle here can either feel an attractive force or a repulsive force, depending on whether the same charge or opposite charges. But the modern description of how that works doesn't pay attention and focus on the charges. It is, what the description uses the electric and magnetic fields, or another field, anyway, the electric field, for instance. And it's called a field because it's something which has a value at every place in space and time.
So it covers an actual area, right?
It's if I say here, I can measure what the electric field is here, okay? And I can make that measurement, and I don't have to see the charge that's generating that field or whatever. I just can put a test charge there and see what force there is on it. So I can say, what's the field here? And so that's a distinction that might not any rate, this is why that kind of description is the natural and best description. I don't know, to me, I didn't really get a gut feeling for this until I was working with a very large electromagnet. Okay, so an electromagnet is a magnet that uses electric current to generate a magnetic field. Now, so the magnet looks the same whether it's on or off.
But the field is not there if it's off.
If the field is that it generates is not there if it's off.
Right.
But if, when the field is on, it has a big effect on things. So for instance, we had an old cathode ray tube, so TV basically in the old days before they were flat panels. And with that technology, you had an actual little electron accelerator in the television tube that rastered across the screen and turned on fluorescent dots. But in the presence of a magnetic field, the electrons felt a force and moved someplace else. So when you turn the magnet on, the TV screen would go like, the picture would rotate. And at any rate,
because that's the magnetic field at work.
Okay, so the description that is actually sort of leads to most insight is to talk about these fields. Now, once you get to looking at elementary particles, you have to bring in quantum mechanics. And the fields actually can be quantized, which is to say that the values that can be taken are not continuous really, but discrete.
So it means that there's a level, like so there's a level 1 or there's a level 2, but there's no 1.5 or 1.75.
And with the electric and magnetic field, the quantum of the field is a photon, which is basically light or other electromagnetic radiation. For the Higgs field, the quantum is the Higgs particle, and it's very different from a photon. And the most sort of obvious difference is that it's massive. It itself has a mass. But the Higgs field still exists every place. Whether or not you're talking about any individual Higgs particles, right? But the effect of the Higgs field in the standard model, so in the theory is it's the best we have, is primarily manifested in the mass of particles that are living in that field.
And it's thought that the Higgs field essentially is imparting that mass to all these other particles, right?
Right.
And I was just reading recently, just to show you how geeked out we get on a show like this, that one of the unanswered questions is the Higgs itself, does it have a structure? So is it something that can be further broken down? Right,
so there you get buzzwords like effective field theory. So the theory in the standard model, the Higgs is a fundamental object and would not have any substructure. But there are various different examples where you can have what appears to be a fundamental force and have it actually be an effect of some other force.
And you only know that through further experimentation, right?
Right. So for instance, neutral atoms don't have any electric charge, and neutral molecules don't have any electric charge, but because of the shape of the charge, they can have chemical interactions with other atoms or molecules.
So you say the shape of the charge, but they don't have a charge.
Well, they have balancing charges. They've got positive and negative.
So
and if the positive and negative are not both perfectly, spherically symmetric, then there can be sort of residual forces. And those residual forces, if you just were to study them at first, you might think that's a fundamental force. And so you could maybe even construct a field theory that would use that would use that force as a fundamental field. But in truth, if you could look more closely at the objects, you'd see that they have substructure, and that that residual force was, you know,
a byproduct.
manifestation of the of the substructure.
So, and this answers another question that I've had about the need to continually get higher energy accelerators to try to create more particles or see if there are more particles. Because one of the things I've read recently is that there's a growing disconnect between the theoretical side of the mathematicians who sit down and figure out these beautiful theories and the experimental side that tries to figure out whether or not these theories actually hold water in the real world. And that particularly you mentioned the standard model, which is, for our viewers, that's I think you described it well. That's just sort of basically how most in the scientific community think things work, right? And it's been developed over decades and seems to predict most things. But for example, I was reading about one element of that, supersymmetry, which was another theory, kind of a branch, but it's never shown up anywhere in any experiments.
Right.
So here's this beautiful theory, but there's no experimental evidence to support that it actually exists. And so it brings up in my mind the question about, well, for a long time, the mathematics were wonderfully predictive, right? You could develop these theories and then you could find them, and if you could build the right experiment, usually you could find that they panned out. And now it seems that that's getting harder to do. Or is that
maybe
not even
yes,
true?
but I think it was never really true.
Okay.
You know, and they're right.
So where do you think that it's not true? I mean, what have there been deviations throughout the study of quantum mechanics or particle physics?
Yeah. Well, I mean, one of the examples that one example is what was called the Bohr model of the atom. So Niels Bohr was a very famous physicist, one of the
Early
sort of
20th
fathers
century.
of quantum mechanics, and the atomic structure had been discovered, and it was known that the electrons in, for instance, a hydrogen atom could only have specific energies, and then so that you can see this because you can absorb light in an atom, but not continuously. Only specific colors can be absorbed, and if you put energy in, for instance, in an arc lamp or something like that, specific kinds of gases will emit specific colors of light, and the colors of light that are emitted have to do with the differences in energy levels of the electrons. So Bohr had what he knew at the time was a sort of a ridiculous idea about how you could
in retrospect, ridiculous, right?
Well, no, I mean there were obvious flaws with it at the time. How you could decide what the energy levels were for an electron in an atom, and that had to do with that it had already been determined that there was that particle moving along effectively also acted in wave-like manner, and that the wavelength of the particle was related to the momentum of the particle, and through what's called Planck's constant. And so that part was known, and Bohr realized that if he just sort of said, okay, the electron with this momentum I know what the wavelength is. It can only live in an orbit, circular orbit, where I can draw a integer number of wavelengths around so that it makes a continuous thing. And if you just do that, you get a model for what the energy levels are of the hydrogen atom, which is actually really close. And it's amazing how well it works. And for highly excited atoms, I mean, it's still the way that people describe, for instance, how big if you have a heavy atom with a whole lot of electrons and you have some of them in a very loosely bound excited state, that thing gets, physically large on a sort of a chemical scale, and really acts as though it's a thing which is the size of the Bohr radius that you'd give to it.
So what was wrong about the this
Well,
model, though.
I mean, one thing is that, remember that charged particles traveling in a magnetic field, feel a force and get deflected.
Mm-hmm.
When they travel in a straight line, they generate a static magnetic field. If you accelerate a charged particle, then it radiates light. And so if you had an electron which was literally circularly orbiting its nucleus, that's a particle which is always accelerating, right? Because it's not going in a straight line.
Right.
So it would radiate light continuously.
Which, in fact,
and lose energy and spiral in.
Which doesn't happen, right?
Right, it's not a stable thing.
Yeah, okay.
So it can't work like that. And Bohr knew it couldn't work like that.
But he loved the model enough.
But he developed the model, and actually the model's useful. It just isn't right.
Now, and that's something else as I read through this that I find remarkable about this level of physics. Things that are known to be wrong or known to be wild guesses or known to have lots of assumptions that no one really believes, but nonetheless they prove to be useful in measurements or more importantly in predictions, right? So I find that a wonderful irony that things that are known to be wrong are still very useful.
Yeah, it's true. It's true. I agree.
Good. So in your research, then, what experiments have you, or do you actually design experiments, or you work with the results of the experiments that are already in existence?
Sort of both.
Okay.
And a lot of my career has actually been focused on developing instrumentation and the electronics that enable the instrumentation.
So, for example, going back to accelerators, so at any of them, CERN, there are all sorts of detectors that will detect this stuff, right? And so that's the kind of thing you're talking about.
That's the kind of thing that, right.
So,
although at different times in my career, I've been focused on, analysis of data, and which these days is, mostly done with computer programs. So. Writing programs.
Yes, I was going to say, someone has to write those programs, right?
That's right.
Right.
Exactly.
So that's part of what you do as well, is write the analysis routines.
I haven't been focused on that in some time, and I'm pretty rusty at it.
and programming techniques have changed a lot as well.
And they have,
So in the commercial world, we read a lot about machine learning, AI, these kind of amorphous terms that basically mean using machines to watch patterns and to develop ideas of how these patterns develop, or what the patterns mean, but just by analyzing huge amounts of data.
Right.
So is that something, I would imagine that's something that's used extensively,
That
right?
is used extensively, yes.
Yeah. And so how has that development of that AI or machine learning changed the way you, for example, think about experimental physics?
Honestly, it hasn't changed the way I think about it at all. And but it has gone from being something which is sort of, in principle, you could do this, to it's the best way to do lots of things. And the big change is just the power of the computers, right?
Sure.
Because
they can do this now, whereas previously it would have been much more difficult.
We have nothing but supercomputers.
Right. Well, that will seem feeble in another 10 or 20 years, right?
Yeah, because Moore's law continues, even though it has been predicted it can't continue for a long, long time.
I think maybe since it came out, it was
just
predicted
about,
that
just about.
it would have a limited life. And for those who don't know, Moore's law is that the power of computers doubles every 18 months. But essentially, that's the basic idea.
And so, since you're with doubling, it's like compounding interest. You get an exponential growth in the power.
Yeah. And so well, actually, we only have about 5 minutes left, but since we're talking about particles and quantum theory, quantum computers, since we've segued into computers. So is that a part of your research at all? Do you look at that?
To first order, no. It's something that is, that FermiLab is actually hoping to get into in a big way. There are a handful of quantum computing initiatives underway at the lab now, and it's one of these things which is sort of a spin-off slash serendipity. Many of the techniques for building a system which can be useful as a quantum computer involve superconducting systems.
Superconducting means there's no resistance. So
Right. If you get some materials cold enough, then the DC resistance to an electric current goes to literally zero. And FermiLab was actually the first place to use superconductivity at a very large scale. The Tevatron accelerator, which was our big accelerator and the main workhorse of FermiLab until the CERN Large Hadron Collider made it obsolete, because it's a similar machine, just bigger. The Tevatron was the first really large superconducting accelerator. So it's, as you said, it's...
And it was the biggest in its day,
yes,
right?
Yeah,
Yes.
for many years was the highest energy machine in the world. But the magnets that guide the particles in their circular path were superconducting magnets. And so there was a fair amount of superconducting technology that was developed for that, the construction of that machine. And then more recently, superconducting radio frequency cavities have become sort of the method of choice for accelerating particles.
A radio frequency cavity.
Yes.
Sounds like something I wouldn't want my dentist to tell me I have. Right.
Yeah, exactly. Okay, so if you have a circular machine, the way that works is that you have a series of magnets, and remember, a charged particle going through a magnetic field feels a force perpendicular to both, and so you can make a force which points to the middle of the circle and keep a particle going in a circle.
Right.
But what you'd like to do is you'd like it to go in the circle and then go through an accelerating structure and gain a little bit of energy, go through the same circle,
Kick it up
gain
again.
a little energy, and of course, in order to keep it in the same circle, you have to increase the magnetic field a little bit each time it goes around.
Okay.
Which, by the way, is the reason these machines have gotten so big, right? Because you want it to get to higher and higher energy, you either have to go to higher and higher magnetic field or just build a bigger circle. And for the most part, the winner is build a bigger circle.
Yeah.
Right.
Yeah.
But you still are accelerating them only in one area.
Yeah.
Now,
So we have like 15 seconds to answer my question.
at any rate, you have to have an oscillating field to do that.
Okay.
And so you have to have a bunched beam. So the beam isn't continuous, it comes in bunches, and you have to time the bunch so it gets an accelerating kick as it goes through the radio frequency cavity and not a decelerating kick or nothing.
So the radio frequency cavity is the kicker.
It's the kicker. It's the accelerating structure.
Gotcha.
Yeah.
Wonderful way of summarizing that in a few seconds.
Okay.
I applaud that. David, it's been such a pleasure to have you here. Thank you so much for being on the show. It's
thank you.
very enlightening for me. So.
That was fun.
And thank you for joining us once again on Public Perspective. I'm your host, Kevin McDermott. You can find us every Saturday night at 8 o'clock on Comcast Channel 19, or see us on the web at publicperspective.tv. So till next time, thank you and good night.